Wednesday next week. Okay, I don't necessarily love the order of this, but this is kind of how our book presents it, is that now we're going to go back and talk trapezoidal rule. Chapter 6 started with all this approximating an area under a curve. And we talked about LRAM, and we talked about RRAM and MRAM. You remember all that, and how we were drawing in those rectangles, and we do base times height and add up all those little areas. Well, it turns out what they find is a lot of times, since it's a curve, is that there's a shape that we can find the area of that actually approximates better than a rectangle, and that is a trapezoid. And so this is what the trapezoid rule looks like, is that, again, it's a shape that we can find the area of using an area formula, but tends to follow along a curve a little bit better than a rectangle does. So if we were to just consider the curve like f of x equals x squared plus 3, estimating the area under the curve from 0 to 4 using trapezoids today, if we just look at that curve from 0 to 3, first of all, we can actually draw pretty accurate what that curve is, since I can just plug in some points here. If I plug in 0 squared is 0 plus 3 would be up 3. And then 1 squared is 1 plus 3 would be up at 4. 2 squared, oops, we're going to run out of room here. I'm going to have to adjust here. That'd be up at 4. 2 squared is 4 plus 3 is 7. And then 3 squared is 9 plus 3 is 12. Let's go up here to 12. So we're looking at that parabola right there. When it says using 4 trapezoids, again, if I kind of consider along here from, oops, I was supposed to go from 0 to 4, wasn't it? And I only went from 0 to 3. Sorry, rewind. Need to add another point in there, and I'm going to run out of room. 7, 12, and then 4 squared would be 16 plus 3, and I really didn't give myself enough room here. 19 would be way up here. There we go. Okay, so from 0 to 4, here we go. Splitting into our 4 rectangles, there'd be half, not rectangles, 4 sections. And in those sections, we're going to draw a trapezoid. So our height of our trapezoid becomes the distance here. And then the 2 bases are what connect up to our function. We've seen these before, but you can see that it's very close to my curve, but it's actually a trapezoid. So like for this first trapezoid that I have drawn here, its area would be 1/2, its height would be the distance between that. Since I had a length of 4 and I split it into 4 equal trapezoids, each of our heights is going to be 1 in this particular example. And then my 2 bases would be at f of 0 and f of 1, so 3 and 4. Questions? So that would be what, 7/2? And we repeat that process all the way across. So my next base, or my next height here, here's the distance between my bases, connect those up to our function. And if I draw in that, there's our little trapezoid. Its height, again, would be the distance between the 2 bases that are going vertical, which is going to be 1 for all of these since they're evenly spaced. And then our 2 bases would be where it hits my function. So f of 1 is 4, and f of 2 was 7. 4 plus 7 is 11, times 1/2 would be 11/2. And keep going. Height of 1. And you can see how it follows my curve a lot closer, right? This is going to be a better approximation than if I was doing rectangles. So now we've got what, 7, and f of 3 is 12. 7 plus 12 is 19 halves. And find the area of your last trapezoid. You're fine. I'm not even worried about that today. Okay, are we having any questions on our trapezoidal approximation? Okay, easy to see when we're visualizing here. Let's see, I don't have my last one on there. 12 plus 19, 31 halves. So then my approximation of the area under the curve would be summing up all of those. Which would be what? Let's see, 20, 30, 68 halves. Check my mental math there. 34. Questions? Okay, just a different shape. Now, transitioning that into our table of data, we have to again consider what shape we are looking at. And we've done this with rectangles, LRAM, RRAM, MRAM, but now what if they were specifically asking you to do trapezoids? Okay, now before we move on to that, our trapezoids, if it is spaced evenly, where you can do your height here, you do not necessarily have to use this rule. You can break it up the way I just did and find the area of each trapezoid individually and add all those up. But if we go back, and I will come back to this page, I promise you. If we go back, what you notice is on each of these, they had something in common because of what our trapezoid is, and because each of our heights were split up evenly, is that each of them had a 1/2 at the beginning, and each of them had the whatever the height is at the beginning of each of those little formulas, right? 1/2 and our height of 1. And so what they're doing is they're factoring out each of those 1/2s and the height because they're all the same. But then if you notice, did you notice that we repeated a lot of the lengths? You repeat the length here to here, right? 4 and 4, 7 and 7, because these sides are shared between those trapezoids, but only the inner sides, right? And then 12 and 12. The ones that are not shared are the 3 and the 19. And so the first base and the very last base. And hopefully that'll explain where this formula is coming from. There's your height times 1/2, right? So they just kind of put it together as one number. They factored that out because it was common to all of them. Our first base and our last base were only used one time, but every base between that was used for 2 different trapezoids, which is why then each of those are multiplied by 2. Okay. So explaining what all these numbers are, your height is going to be the length of your interval divided by however many trapezoids we are making, which we've just kind of been figuring out our own, not something you have to memorize, right? We can figure that out. It is worth noting that your trapezoidal approximation will be the average of your LRAM and your RRAM. So using this for a little bit uglier version, if they ask us to use the trapezoidal rule, let's go ahead and try it out this way instead of drawing out each of our different trapezoids, finding the area of each of our trapezoids. It says use the trap rule to estimate from 1 to 2 x squared dx. So let's try without drawing it. Okay, our trapezoidal rule, but it asks us to break it into 4 trapezoids. So I can figure that out by just considering the distance between 1 and 2 and dividing by 4, but I can also use our height up here. The height would be the difference in our interval, 2 minus 1 divided by however many trapezoids I'm trying to make. 2 minus 1 is 1, divided by 4 is 1/4. And then what these numbers are is evaluating your function at each of the different places. So we should have 4 different places along there that we are evaluating at this, starting at 1 to 2, a difference of 1/4 each time. Okay, so I'm going to come over here and kind of lay that out for us, is that we are evaluating this at our a sub whatever n into our function up here, which is x squared. So we would start at 1. We are going to work our way up to 2. Okay, and our first, so then we would, but we're only moving a distance of 1/4 each time. So 1.25, 1.5, 1.75, and 2. Okay, grab your calculators real quick. Our function is x squared. So we're going to square each of those. I don't know what 1.25 and 1.75 squared are off the top of my head. What's 1.25 squared? Am I right on the 1.5 squared? 2.25. What's 1.75 squared? Is that what you said? All right, so then putting those into my formula. So this would be a sub 0 here, a sub 1, a sub 2, a sub 3, a sub 4. We don't necessarily need to recognize that, but so you kind of understand where they're falling, is that the first and last will only be used one time, but all the ones in the middle will get multiplied by 2 because it would have been the base for 2 different trapezoids. So our trap approximation would be our height, which is 1/4, divided by 2, times our first base plus 2 times our second base plus 2 times our third base plus 2 times our fourth. Oops, I'm going to run out of room here. And then our last base is only used once. First and last should only be used one time because they are not used for 2 different trapezoids if you were to draw that picture. And we type all that into our calculator. And this definitely is a calculator problem. And to speed up our process, we should be getting, let's see, 2.344. I did not on mine, I did not round these in here, so I don't know if that put us off or not. You don't have to go off to the side and figure out what those are. You can. I could have done it within here. Is just plug it into the function in the middle of it as well, right? I could just type in 1.25 squared right here. Questions? Okay. You are frequently asked if something is an overestimate or an underestimate, and this is not specific to our trapezoidal rule, but one of the things you can consider is my function concave up or concave down at that time? And as I connect those points on there, as I'm drawing this, would that my trapezoid fall above or below? And the hard part is if we have a lot of trapezoids in there, it gets so close to our function, it's hard to see, right? But if you were to consider a concave down function, and let's just kind of exaggerate this, if I only drew 2 trapezoids in there, let's say it went to right here, can you see that as I connect those, it would go slightly under my curve? So if I'm talking a concave down function, my second derivative being negative, concave down, that my trapezoidal rule here would be an underestimate. Compared to if I had a concave up function. Again, I'm just going to break this into two trapezoids here so that it's a little easier to see as I connect those two to make my trapezoid, that I get this little bit of space above the curve. And so then I would say that this is an overestimate. So when you are asked about whether what you just created was an over or an underestimate, what you can do is consider if you're looking at a concave up or a concave down function. For example, if we went back here, just because we really know the function x squared, concave up, right? So did our trapezoidal rule just give us an over or an underestimate for that? Well, looking at what we just looked on the last page, we would say that we just had an overestimate, right? Our trapezoids would be slightly above that curve. Questions on that? And that goes kind of for all of your questions. It doesn't, again, necessarily talk about trapezoids. If we were to consider like a concave down function, look at the difference between doing like an LRAM versus an RRAM for a concave down function. And you can give yourself these little pictures to look at. If I do a concave down and I'm doing an LRAM, do you see how I get that big overestimate? Compared to, again, if I just do like two rectangles here and I do an RRAM, actually that would be right there, that we get an underestimate. So give yourself kind of a generic picture to look at what type are you using, trapezoids, LRAM, RRAM, to see and consider the concavity of your function at that time. Questions? All right. Do one example here. All right, in this example, we are given the integral from 0 to pi of sine of x dx. It says use the trap rule with n equals 4, so 4 trapezoids, to approximate the value of the integral. And you're going to use the concavity of the function to decide if you have an over or an underestimate. And then we'll use our calculator to check our integral's answer. Since this is practicing what you just saw, try it on your own before I jump into how to do this one. For part B, think about what you know about the picture of sine of x. Help you decide if you just over or underestimated it, and then remember on your calculator where you find an integral's exact value. Okay, part A, use the trap rule with n equals 4 to approximate the value of the integral. First of all, to figure out what our height is, our interval is from 0 to pi, so pi minus 0 over 4 would be pi over 4. If it helps you to draw the table off to the side so you can see working your way from 0 to pi, one pi over 4 at a time, you can do that to see what those values would be. Our function being sine of x. So starting at 0, adding a pi over 4 each time, we'd be at pi over 4, pi over 2, 3 pi over 4, and pi. Plugging that into our sine of x is where we got to remember our unit circle a little bit. Sine of 0, 0, sine of pi over 4, square root of 2 over 2. Your calculator will give you a decimal approximation of that, so whatever that is decimal wise. Sine of pi over 2 would be 1. Sine of 3 pi over 4 would be square root of 2 over 2. Square root of 2 over 2. And square root of pi is 0. And then I put that into my trap rule. That says our trapezoidal approximation is going to be our height. This is the part people forget, divided by 2. Remember, it's 1/2 times the height, right? Or our height divided by 2 is that thing we factored out from each of those trapezoids at the beginning, times our first base, which is 0, and then 2 times each of our other bases. And you might have decimals at this point here. And then just 1 times our last base here. And whatever that ends up being is a decimal. 1.896. Any questions so far? Okay, part B. If I consider the sine curve, a sine curve looks like this, goes out to 2 pi, here would be pi. So we're really just focused on from 0 to pi, which would be this part, is concave down, right? And if I were to draw a trapezoid in a concave down portion, that it would be an underestimate. So that tells me, because it is concave down, that this was an underestimate. So then part C, we actually just go to math 9 this. Type that in my calculator, making sure my physics people that we are in radian mode when we do that. And we should get an answer of 2. So check, we approximated it at 1.896. We said that's an underestimate. The actual value is 2. All of that meshes together. Questions? Okay, sticking with the idea of trapezoids, how do we then transition that into a table of values? We've seen this again using like LRAM and RRAM and MRAM. How do we use it with a trapezoidal approximation? So an observer measures the outside temperature every hour from noon here until midnight here, every hour. So 1 p.m., 2 p.m., 3 p.m. till midnight, recording the temperatures in the following table. What is the average temperature? What is the average of this function? So this is a little twist on just finding the area under the curve. Remember that the average of a function is 1 over b minus a times the integral from a to b of that function. That's what it's asking us to do, right? What is the average of a function? 1 over b minus a times the integral of that function on that interval. So for the 12-hour period, it would be 1 over, and this is a little bit tricky if we want to consider this then military time, if you want to call this like 12 o'clock and this 24. Ultimately, we need this to be 1 over, what's the difference between those? 12, right? 1 over 12 here. Or if you want to call this 0 and this 12, we can do that, okay? So then our integral, we'll call it 0 and 12. Of our function, we'll call it temperature at time t dt. So what we're going to use today, since we're talking trapezoidal, is we're going to use a trapezoidal approximation for the area here. Okay. So when doing a trapezoidal approximation in a table, remember that if I were to graph this right here is the height of our trapezoid. This would be base 1 and this would be base 2, right? So if I put that into our trap rule here, that this can be approximated as our height, which is 1 over 2, right? Times our first base plus 2 times all of our middle bases plus the last base solo. Yes, so I don't have to find the area of each of those trapezoids individually. I can use that trap rule. Are we all okay with that? Okay, so grab your calculators and start typing. Remember, your first base and your last base will only be used one time. All the others are times 2. And then it was the average, which is why we have this out here. So I'm going to put that 1/12 out front also. When you get done with this, the average temperature, if you look at those temperatures, 63, 65, up to like a 70, down to a 55, obviously our average is going to be somewhere between that 55 to 70 range. And if it doesn't end up falling in there, we'll probably type something into our calculator wrong. Okay, let's see how accurate you were typing things into your calculator. What do we get for what's in the green here? You should have 782, giving us an approximate or an average temperature of 65.167. Questions on how to use the trap rule with a table of data? Okay. A visual and using our trap rule here. It says a surveyor wants to find the total area in this lake. He takes measurements using GPS every 100 yards. So starting here to here, the distance between those measurements is 100 yards, distance here, 100 yards, all the way across this lake. Estimate the total area using trap. The first one is not super obvious, but I'll draw it with the second one. So our height of each of these trapezoids is going to be 100. There's your trapezoid right there. You've got kind of a function on the top and the bottom, and that's okay. Our bases would be the 52.3 and the 68.1, with your height being 100. Okay, all the way across, your height's 100. Your bases are listed in the picture. So if we were to use our trap rule, our height is 100. Right, that's your height, is 100 divided, always divided by 2 for the 1/2 times the height, times, and then the trap rule says the first base, which is 0, will only be used once. All the rest of the bases will be used with 2 different trapezoids. So 2 times 52.3 plus 2 times 68.1. You can, if you see this, factor out your 2 right here and just add up all of those inner bases, just not the first and the last, right? Kind of speed things up in your calculator so you don't have to take times 2 times each of those. Your last base should be 0. So again, just creating trapezoids in that picture. This time we just had a function on the top and the bottom, just not a straight line along the bottom, which is fine. Any questions for me? Easy enough. And your approximation using your trapezoids in this picture, again, seeing how accurate we are with our typing in of our calculator. You should get 56,530. Okay. And then think about what we just found. It said estimate the total area. So total area, I would be labeling this as yards squared. Questions? All right, our last thing we're going to talk about today is what's called the Simpson's rule. Simpson's rule, it gives us a different approximation for, or a different formula to do the approximation of the area under the curve. However, it doesn't work all the time. It's only going to work if your interval from A to B is partitioned into an even number of intervals. And if it is partitioned into an even number of intervals, which we've seen all today, right, 4 trapezoids or whatever, that this Simpson's rule can apply. If they're not equal or it's not an even number of intervals, this would not work because of how it is designed, okay? It looks very similar to our trapezoid rule. The thing that changes is your height is now divided by 3. Notice your first and last base or your first and last function value are still only in there one time. But then starting with a 4, it alternates 4 times 2 times 4 times 2, and it will continue alternating those all the way through your setup. Okay, so let's do one example to show you how to do this. It says use the Simpson's rule to estimate the integral from 0 to 2 of 5x to the 4th dx using n equals 4. When would I use Simpson's rule? If they specifically told me to. Okay, does it work if it's an even number? Yes, I probably wouldn't think to use it. Not something I'm going to spend a lot of time working with or memorizing, but I would attack this very similarly. Okay, so if n equals 4, the height is going to be 2 minus 0 divided by 4, 2 over 4 or 1/2, which means my function values, which they call y sub whatever, and my function is 5x to the 4th, would go from 0 to 2, adding 1/2 each time. So 0.5, 1, 1.5, and 2. And I'm going to plug each of those in to 5x to the 4th. So for example, 0 here, 5, you guys are filling in the rest for me. Okay, so using our Simpsons rule here, oh, let me fill in the rest of this table. So 0.3125, 25.3125, and 80. If you like the table setup, go right ahead and do that. You can also just evaluate the function within the setup. So let me show you how I could do that as well. So my rule says the first and last are only used one time. So my first base was 0. And then we start with a 4 times my first value plus 2 times my next value plus 4 times my next value plus our last base only used one time. Okay, and I can plug them in here, or I can just evaluate. So I can type in the 5 times 0.5 to the 4th right here, or fill in the numbers here. 5 times 1.5 to the 4th. Oops, that was 1. Darn it. So you don't have to do a special table off to the side. Like I could do right here, 5 times 1.5 to the 4th. I can type all that in and save myself a little bit of time as well. Just for the visualization purposes of it, I was doing a table off to the side. And if we type this into our calculator correctly, we should be getting approximately 32.083. Any questions for me today on trapezoidal rule? Okay. Your assignment tonight is on page 316. You are doing 1 through 10 and then 13 through 18.